Okay, well, I think we'll get started because we're a few minutes after 9. So, welcome everybody. Good morning, afternoon, evening from wherever you're joining the globe. My name is Jamie Tricker, so I'm the Deputy Director of the Sydney Infectious Diseases Institute, and we look after infectious disease research across the University of Sydney. And together with Ben Murray, our Director, I'd like to welcome you to this distinguished lecture series. So firstly, I'd like to acknowledge the traditional custodians of the land we meet on, which is the Gadigal people of the Eora Nation, and I pay my respects to elders past and present and extend that respect to all Aboriginal and Torres Strait Islanders that may be joining us here today. So it's my great pleasure to introduce today's speaker, Dr. Dan Barouch. Dan is currently the William Bosworth Castle Professor of Medicine at the Harvard Medical School, and he is the director, I think the founding director of the Center for Virology and Vaccine Research at the Beth Israel Deaconess Medical Center, which is also at the Harvard Medical School. Dan is a graduate of Oxford University and received his PhD and he received his MD from Harvard. And I think it's fair to say many of you online will know of Dan's work and be aware that Dan has really transformed global vaccine research. In particular, his pioneering work on viral vaccine platforms, and he has a long list of achievements in this area, and that's what we'll hear about today. But I think by way of introduction, I just wanted to say that when Dan agreed to give this seminar, I gave a little fist pump in the office. I was very excited, and really the reason is that those of us such as myself who are working on vaccine development, and we're in the laboratory looking at antigen discovery and developing new vaccine platforms. I think the ultimate outcome for us is for that work to be translated into something that has a real impact on human health. And I think Dan's work has been inspirational because this is what he's done. He's been able to combine very high impact research, and we were just talking about a new article that's coming out soon in Cell on his TB work. But also translate that into products that have saved many lives. And this is what we saw, particularly through COVID with his work with Janssen and Johnson & Johnson on their viral vaccine platform. And I think that vaccine has been used in over 130 countries. So we're really delighted to have Dan here today to hear his work on respiratory vaccines. And I'll hand over to you, Dan. Thank you.
Well, thank you, Jamie. Thanks for the warm introduction. Let me share my screen. Okay, can you see my slide okay?
Yep, that's great. Thank you.
Okay, great. Well, thank you all for joining. Thanks, Jamie, and for the Institute. It's a pleasure to be here today. I really enjoyed my last visit to Sydney and Melbourne, although that was pre-pandemic times, and hope to come visit in person at some point in time. What I'd like to do over the next 35-40 minutes is to talk about some of our recent work on correlates of protection for respiratory virus vaccines. In other words, what immune responses are really critical for protection against a virus that uses the mucosal portal of entry. And then there should be plenty of time for questions and discussion at the end of the hour. So here are my disclosures. So it's estimated that over 20 million lives have been saved by the COVID-19 vaccines in the year 2021 alone, led by the AstraZeneca-Oxford vaccine and the Pfizer-BioNTech vaccine, but also contributions from the Sinovac, Moderna, Sinopharm, Sputnik, J&J, Brad Biotech, and CanSino vaccine, and others, which is truly a historic accomplishment of biomedical science. But there are some issues and downsides with the COVID-19 vaccines that I think we need to be aware of to make better vaccines in the future. So this is data not from our lab, but from the North Carolina Department of Public Health and about 10 million people, in which they looked at during the 2022-2023 era on protection against hospitalization and protection against infection. And this encapsulates a difference that I think many groups have seen, and also I think many people in their lives have seen, which is that the COVID-19 vaccines provide excellent protection against severe disease. It does wane over time, but it's sort of 64% that wanes to the 40s. However, the current COVID-19 vaccines provide much lower level of protection against acquisition of infection and mild respiratory disease, here estimated at 30% and going down to 0% within 16 weeks. So we wanted to ask the question, why is this difference? So why do the current COVID-19 vaccines provide robust protection against severe disease, hospitalization, and death, which is obviously a critical, important aspect of vaccines, but why do they really not provide very good protection against infection? So we had a hypothesis that intramuscular vaccination typically does not induce mucosal immunity, and that if there were a way to improve mucosal immunity, then one could improve the protective efficacy of respiratory virus vaccines. So to address this question, we did a study that was published last year. So I'll talk briefly about this published study. And then I'll conclude with some of our work on influenza that is recently published in press and not yet published, unpublished data. So this study, which was published last year, we demonstrated that mucosal boosting enhances vaccine protection against SARS-CoV-2 in a macaque model. And in this study, we had a cohort of rhesus macaques that we essentially had over the last 2 years as part of our collaboration with J&J in the development of the Ad26 COVID-19 vaccine. This particular cohort of animals was primed 2 years prior to the beginning of this study and was boosted approximately a year prior to this study. And then at the start of this study, we decided to compare different routes of boosting. So we gave another injection of the Ad26 vaccine by the intramuscular, intranasal, or intratracheal routes. Here, intranasal was just drops in the nose, intratracheal was just drops in the lung, but we would envision a nasal spray in humans would probably approximate the intratracheal route here. We also compared this with an mRNA vaccine given intranasally, as well as a group that did not receive a boost. And then we added on 7 additional animals that were sham naive controls that were essentially challenge controls. And so this study started essentially with differential boosting. So in the publication, we have exhaustive amounts of immunologic data. I'm not going to show that here based on time and because it's a published paper. But all of these modalities raised serum antibodies to very high levels. So a substantial boost by all routes of boosting, intramuscular, intranasal, and intratracheal. That's not shown in this slide. What is shown in this slide is the mucosal antibodies. So the mucosal antibodies in bronchoalveolar lavage and in nasal swabs. You can see here, if we give an Ad26 vaccine boost by the intramuscular route, then we really do not see, or we see a relatively modest increase in mucosal neutralizing antibodies in BAL nasal swabs. This is only slightly better if we give by the intranasal route. But if we give the vaccine further down in the respiratory tract, here experimentally as an intratracheal vaccination, here shown on the right, and we see this vast increase, really just a black and white result, this vast increase in high titers, consistent cross-reactive neutralizing antibodies in the lung as well as in nasal swabs. So basically, here we show that if you give the vaccine mucosally, then we see a dramatic enhancement of mucosal neutralizing antibody responses. If we look at mucosal IgA binding antibodies, it's even more black and white, that an intramuscular boost raises only very low and transient mucosal IgA and BAL nasal swabs. This is only slightly better given intranasally, but if we give the same vaccine intratracheally, then we see this high titer and consistent and relatively durable mucosal IgA. If we look at T-cell responses, we see the same thing. So if we give the boost by the intramuscular route and we look at T-cell responses, now these are not peripheral T-cell responses. Peripheral blood T-cell responses, which is shown in the paper, are high frequency for all boosted groups. So all of these boosts raise high-frequency T cell responses in peripheral blood. Here we're looking at T cell responses in bronchoalveolar lavage. Experimentally, this is done as high-volume bronchoalveolar lavage in which we can isolate cells from the BAL, and we basically have just enough cells to do one tube of intracellular cytokine staining, which is why we can only test for one strain. But basically, if we look at CD8 responses on the top and CD4 responses on the bottom in lung, or rather in BAL, then the intramuscular vaccine raises low and transient mucosal CD8 T cells and really no CD4 T cell responses. This is only slightly improved if we give the vaccine intranasally, but if we give the vaccine intratracheally, then we see high frequency and sustained CD8 and CD4 T cell responses in lung. This is really a black and white difference, which is the magnitude and the separation between the intramuscular and the intratracheal routes is really astonishing. So then we challenged these animals with SARS-CoV-2, and we saw that the protection basically reflected the mucosal immune responses. If we go counterclockwise and we look at the concurrent sham controls, then we have 5 or 6 logs of virus seen in BAL on day 2 following challenge, and it's controlled in about 10 days. In the group of animals that was not boosted, we still saw a reduction of peak virus from about 5 logs to about 4 logs. So we still saw about a 10-fold reduction in peak viral loads compared to sham controls, showing long-term durability of some level of protection. Now, I didn't show you the immunogenicity data, but if we give an mRNA vaccine mucosally, it really just doesn't work because we think that the current mRNA LNP vaccines don't have the biophysical stability to survive in mucosal surfaces. And my colleagues at Moderna and Pfizer agree with this. And those mRNAs are being formulated for potential mucosal delivery, but that's not the currently available vaccine today. If we give the Ad26 vaccine intramuscularly, we see some suppression of virus compared to the no boost group. This is improved somewhat by the intranasal route, and it's improved markedly by the intratracheal route, so that here only one animal showed a blip of virus for 1 day. Otherwise, the Ad26 IT group came close to protection. What we called it is near complete protection against acquisition of infection. If we look at viral loads in nasal swabs, we see a similar phenomenon. We see high titers of virus in the sham controls of about 5 logs. That takes about 14 days to control. In the no boost group, this is reduced by about a log. The mRNA boost didn't really do much. The Ad26 IM boost only reduced this somewhat. This is a little bit better by the intranasal boost. And the intratracheal boost, then we only saw a blip of virus for 1 day in most of the animals. In one animal, it was on 2 days. And this blip on day 1, we think is mostly input challenge virus. And so it's not really clear that any of this is newly replicating virus. So we concluded that if we boost mucosally, we can achieve near complete protection against acquisition of infection, whereas any boost, even robust boosts intramuscularly, while they can protect against severe disease, they really do not protect against acquisition of infection. If we do a high-dimensional statistical analysis, a multivariate statistical analysis, then the correlates of protection against challenge really cluster. The top 3 correlates are the antibody and the T cell responses in BAL. So now, if we look in humans, this is a study that we published again last year, and we have this is based on the XBB mRNA boosters. This is a human cohort study now. And we have very similar data with last year's season with the KP2 vaccine. Then in this cohort in humans, we looked at responses before and after vaccination in peripheral blood as well as in nasal swabs. And here, like many other groups that have been tracking the immunogenicity of the clinical mRNA boosters, then we see that the mRNA XBB.1.5 vaccines made by Pfizer and Moderna all raised substantial neutralizing antibodies in serum, including boosts of all variants that were current at that point in time up to JN1. However, if we look at boosting in nasal swabs, then we see that it doesn't do anything at all. The intramuscular mRNA vaccines in humans really do not boost mucosal responses at all in humans. So this is very similar to what we saw in monkeys. And We had a sub-cohort where a few people had intermittent COVID-19 infection during the time period of this study, and those people did have high levels of mucosal antibodies in humans, and so that's also in the paper. But here, the intramuscular vaccine really did not boost mucosal neutralizing antibodies at all. So briefly, to conclude this part of the talk, I didn't show all the immune data, but some of our published work suggests that data from macaques and humans suggests that both antibodies and T cells, and not antibodies alone, are important for vaccine protection. Short-term antibody responses are important, but the durability of neutralizing antibody and T cell responses are critical for protection against severe disease with the variants. The bivalent boosters were limited by immune imprinting to the ancestral strain, and the monovalent boosters overcome this problem. And then the data I concentrated mostly on was showing you that current intramuscular vaccines really do not boost mucosal immunity for SARS-CoV-2 vaccines. And mucosal boosting is required for enhancement of protection, including protection against acquisition of infection, or at least near complete protection against infection in macaques. So I'll switch now to talking about influenza. We wanted to try to apply these concepts that we learned from SARS-CoV-2 to another respiratory mucosal virus. So we naturally turned towards influenza. We wanted to see if the requirement of mucosal immunity for enhanced protection would be seen for a second respiratory viral pathogen. So seasonal influenza is an unmet medical need. There's 300 to 600,000 deaths worldwide. In the United States, 12,000 to 61,000 deaths. And current clinically licensed vaccines are typically the inactivated virus vaccine. So a year ago, it was when we started, or a year and a half ago when we started the study, it was a quadrivalent inactivated virus vaccine. Now it's a trivalent inactivated virus vaccine. So this study used the QIV as an intramuscular vaccine. And there's also a live attenuated vaccine called FluMist, which was a quadrivalent live attenuated vaccine given by the intranasal route. All the other platforms are research platforms. There's also a substantial need for better influenza vaccines. This is the performance of influenza vaccines over the last 15 years, according to the CDC. And you can see it ranges from 19 to 60%. On a typical year, it's about 40-45%, which I think has been the case for the last 2 years. So while this is a substantial degree of effectiveness, then there's also a substantial room for improvement. And we would, of course, rather have a vaccine that's 80, 90, or 99% effective rather than the vaccine that's 45% effective. So we performed a comparative influenza study in non-human primates, which was just published a couple months ago. And the goal of this study was to compare the immunogenicity and the protective efficacy of systemic versus mucosal boosting strategies for influenza vaccines. This study used 42 cynomolgus macaques, 6 per group, and essentially as a poor person's approach to inducing some influenza immunity, we gave all the groups the QIV vaccine to start with at week 0. This was not really meant as a vaccine prime. This was really intended to give a degree of influenza immunity to all the animals as a starting point. Now, clearly, that is not the same as a lifetime of human exposure, but it's sort of better than naive animals. Then the real experiment was the single boost at week 8. So the single boost at week 8 was a comparison of platforms and a comparison of routes. So we used our Rhesus Ad52 vaccine, a prototype adenoviral platform, given intramuscularly, intranasally, and intratracheally, just like we did for the SARS-CoV-2 study last year. Intramuscular was just stand on needle and syringe. Intranasal is just drops in the nose. Intratracheal is just drops in the trachea. We would envision that a robust nasal spray would probably achieve closer to the intratracheal routes than just the intranasal routes. We also collaborated with Pfizer on this study, and Pfizer provided their mRNA flu vaccine, which I believe is in phase 3 studies or maybe is approved or soon to be approved, as a comparator of a novel approach. So we have 2 novel gene delivery approaches, an adenovector and an mRNA. And then these were compared head to head with the two clinically licensed vaccines, QIV given intramuscularly and FluMist given intranasally. So basically, we have the clinically licensed intramuscular and mucosal vaccines, and they're compared against the gene-based vaccines given intramuscularly or mucosally. And then at week 20, we do an H1N1 challenge with 10 to the 6 TCID50 of the Wisconsin strain given intranasally plus intratracheally, which is our standard challenge route for SARS-CoV-2 and influenza. I should mention that the RAD52 and the mRNA vaccines did express the H1 of the Wisconsin strain, so it is a homologous challenge. So again, this article has a wealth of immunogenicity data. I'm just going to show some select slides just to make some points, but there's a lot more immunogenicity data in the articles that are published. So here are serum neutralizing antibodies, and if we go sort of counterclockwise, if we look at the boost, which is essentially the differential boost that you see on the top, then the FluMist had only a mild boosting effect, minimal actually. A QIV boost increased serum neutralizing antibodies by about a log, which is about the expected amount. We saw a substantially higher boost when we give an mRNA vaccine or a RAD52 vaccine. This is about 2 logs higher, a 2-log boost. So both of these platforms are intrinsically about 10-fold more potent than the QIV clinically licensed vaccine. Now, interestingly, if we give the RAD52 vaccine by the intranasal and the intratracheal routes, we also get a substantial boost. So here we're showing that mucosal delivery of the vaccine actually boosts serum responses almost as much as intramuscular boosting does. So by giving these vaccines mucosally, you don't really lose much in terms of the serum neutralizing antibody response if you think that that is important. But if you look at the mucosal antibody response, and here we're looking at IgA responses in bronchoalveolar lavage, then you see a picture that is completely different. And this is the same sort of black and white difference that we saw with the COVID-19 vaccine data. Here, the clinically licensed vaccines, including FluMist and QIV, induced 0, so no detectable mucosal IgA whatsoever. So just a flat 0. There was a very, very low levels and inconsistent mucosal IgA induced by the mRNA and the RAD52 vaccines given intramuscularly. We see more robust responses, the RAD52 intranasally, and we see robust and relatively consistent and durable responses of IgA in BAL when we give the RAD52 vaccine intratracheally. So we can see that similar to what we saw for COVID-19, if we give an advector mucosally, then we get a very robust mucosal immune response. If we look at CD8 T cell responses, then we see a similar phenomenon. So here we're not looking at CD8 T cell responses in peripheral blood. All of these raise CD8, well, actually not, the QIV didn't, but all the gene-based vaccines raised robust CD8 T cell responses in peripheral blood. Here we're looking at CD8 T cell responses in the bronchoalveolar lavage. The clinically licensed vaccines raised absolutely 0, so they did not induce any CD8 T cell responses in the lung at all. There were inconsistent but occasionally detectable CD8 T cell responses induced by the mRNA vaccine. With the RAD52 vaccine, advectors really do generate better CD8 responses than mRNA. We did see robust CD8 T cell responses in peripheral blood, but it waned quickly over time. This was slightly better intranasally, but if we give the vaccine intratracheally, we see high frequency and sustained CD8 T cell responses in lung. So now if we look at protection against H1N1 flu challenge, and here are viral loads in bronchoalveolar lavage. In the sham controls, we have 7 logs of virus peaking within about 2 days, and this is controlled in about 10 to 14 days. If we look at the clinically licensed vaccines, the FluMist intranasal boost or the QIV intramuscular boost, these actually didn't do much. They had maybe about a 1 log reduction of peak viral loads. So basically, the clinically licensed vaccines did not really have a very marked protective effect in this high stringency challenge model, which actually I think is consistent with the fact that these vaccines really do not work very well in humans. If we look at the intramuscular mRNA or the intramuscular Rad52, we get a marked improvement in protection. And this improvement is better when we give it intranasally, and is particularly better when we give the vaccine intratracheally, where most of the animals do register some virus, but it's very low, typically at about a 3 log level, and it's controlled in about 4 days. If we look at virus and nasal swabs, then we see a similar phenomenon that we see high amounts of virus and nasal swabs in the sham controls, about 7 logs of virus. That takes about 14 days to control. We see a modest reduction of virus by the clinically licensed vaccines, but nothing really to speak home of. If we give the mRNA or the Rad52 vaccine intramuscularly, we see a reduction of viral loads to about 4 logs and more rapid control. And this is improved by the intranasal route. And with the intratracheal route, then we have some animals that don't show any virus at all, and most animals that really only show 1 day of virus. And in the majority of animals, all except for 2, then virus is controlled by day 2. So if we look at the correlates of protection, first looking only at the clinically licensed vaccines, the QIV and the FluMist vaccines, and here the way these heat maps are done, we have a variety of immune parameters on the y-axis, ranging from serum to mucosal antibody responses, as well as peripheral and mucosal T-cell responses. And we look at what correlates with day 2 virus in BAL, day 2 virus in nasal swabs, time to virologic control in BAL, or time to virologic control in nasal swabs. Then we see that for the clinically licensed vaccines, it's really serum antibody responses that correlate. And that's sort of very consistent with the literature. And it's also not a surprise because those are the only responses induced by these vaccines. These vaccines really do not induce T-cell responses and really do not induce mucosal responses. So here we see that the serum binding antibodies and serum neutralizing antibodies are really the correlates of protection. If we look at the total study, though, then we see something more complex. If we look at either all animals or all vaccinated animals, we see a much richer correlates of protection analysis, where we see that the serum antibodies and the mucosal antibodies all correlate with protection, and we see the mucosal T-cell responses also correlate with protection. Interestingly, the peripheral blood T-cell responses did not correlate with protection, and we're still trying to sort this out. But basically, we're seeing both antibody and T-cell responses in the periphery, and antibody responses in the periphery and antibody and T-cell responses in the mucosa correlate with protection for the study as a whole. So the third short story I'll tell you about is the third test of this concept, which is we did on H5N1 flu. As I'm sure you know, there's been an outbreak of H5N1 avian flu, clade 2.3.4.4b, in dairy, cattle, and poultry. There's been approximately 70 cases in humans to date. Most have been clinically mild, but there have been several severe and a couple lethal cases. We think that most are clinically mild because currently the virus has bovine adaptation mutations and has not yet acquired the capacity for person-to-person transmission. But we do think that H5N1 poses a significant pandemic threat for humans because we know that these cassettes are interchangeable, and influenza has been able to exchange out adaptation mutations to allow for increased human pathogenicity and transmission. And the fact that the virus was able to adapt to another mammalian species, namely cows, is notable, and that's what caught people's attention, that this was not restricted just to birds, but also made the jump to at least one mammal species. So over the last year, we've had 2 objectives. We wanted to develop an H5N1 challenge model in non-human primates, and then we wanted to evaluate vaccines, antibodies, and therapeutics. So we developed a model of H5N1 infection in cynomolgus macaques, and this paper was just published last month in Immunity. And I'm just going to show this one slide to show that this is actually a highly pathogenic, lethal challenge model. And in this paper, we have histopathology and clinical descriptions and many other aspects of this. But basically, we infected 24 cynomolgus macaques with a dose titration of 10 to the 9, 8, 7, and 6 of an H5N1 challenge stock. And all the animals died between day 4 and day 7 following challenge. It was really stunning. We did not expect this because the H1N1 challenge model is a non-lethal model, whereas as I showed, we have virologic endpoints, but we don't have clinical endpoints. The animals don't get sick for H1N1, and they certainly don't die. Here, these animals died of rapid respiratory failure, and histopathology and PET scanning confirmed that these animals died of severe overwhelming pneumonia. Here on the right, you can see clinical. On the left is the Kaplan-Meier curve showing the rapid progression of disease, and on the right is a clinical scoring system for semi-quantitative measurements of clinical disease. And you can just see that this is a very different virus. So based on this, then I certainly personally really hope that H5N1 does not acquire human pathogenicity criteria. So the vaccine study that we did in cynomolgus macaques is the following. And you can see thematically, this is very similar to the COVID-19 study and to the H1N1 study. We really wanted to see if vaccines would protect against H5N1, and we wanted to see if mucosal boosting would be beneficial. So this study involved 4 groups. The first group received an mRNA vaccine expressing the H5N1. It's actually the H5 immunogen from H5N1 Texas, as 2 intramuscular shots, a Rad52 vaccine given as 2 intramuscular shots, and a third group that received a prime intramuscular and then a boost by the intratracheal route, given our learnings from the prior 2 studies. We stopped trying to give the mRNA nasally or intratracheally because it just doesn't work. So these animals received 30 micrograms of the mRNA vaccine or 10 to the 11th viral particles of the ad vector, prime at week 0 and boosted at week 8, intramuscular or intratracheal. And then at week 16, we did a challenge with 10 to the 6 TCID50 of the H5N1 challenge stock that we developed in the prior paper. So here are serum antibody responses. So IgG responses to either H5 Texas on the top or H5 Astrakhan on the bottom, 2 different H5N1 strains. Simple ELISA binding antibodies. And we show here that all 3 vaccine groups raise binding antibodies after the first immunization at week 4 and week 8. And at week 8, they received a boost, and all 3 groups had a substantial boost in titers of these antibodies to about 5 logs, and very similar in all 3 groups at week 10, and this persisted through week 17, which was just before challenge. Here, I'll note that the mRNA and the Rad52 vaccine given intramuscularly were approximately similar in potency. So we view these platforms as similarly potent. And when we gave the Rad52 boost by the intratracheal route shown in blue, we boosted serum responses just as well as if we gave it intramuscularly. So similar to the H1N1 study that I made a point of, if we give the vaccine mucosally, you don't lose anything. You get the same serum antibody boost as if you were to give it intramuscularly. So there's really no downside in giving the vaccine by a mucosal route. You can see here in serum, the blue responses, the IT boost, were just as high, even slightly higher than the intramuscular responses. Now, it's not significantly higher. We call these essentially equivalent. But certainly, the intramuscular boost did not result in any lower serum responses. But when we look in the mucosa, then it's again this black and white difference. So if we look at IgG in the mucosa, then we see after the boost, which is at week 8, we see a substantial increase in the mucosal BAL IgG responses in the intratracheal group shown in blue. We do see low levels of IgG in the mucosa with the intramuscularly boosted groups. But when we look at IgA, we see exclusively responses in the IT boosted group. We think this is because IgA has to be primed locally, whereas IgG, there is a inefficient translocation of serum antibodies to the mucosa for IgG, but not for IgA. So we see these very low levels of mucosal IgG following an intramuscular boost, but we see essentially no IgA and virtually no neutralizing antibodies with the intramuscular boost. So this is all very similar to the last two studies. If we look at T cell responses in peripheral blood, then we know the mRNA vaccines give low levels of T cell responses. Advectors generally give better CD4 and CD8 T cell responses than mRNA vaccines, and you can see that here as a trend at least. But if we look at T cell responses in the BAL, is here we look at gated CD4 T resident memory cells and CD8 T resident memory cells in BAL at week 10, then these are exclusively seen in the RAD52 intratracheally boosted group. There's really flat zero responses given either of these vaccines intramuscularly, and we see 100% responders for CD4 and 4 out of 6 responders for CD8 for resident memory T cell responses in BAL following the boost. So now, post-challenge, this is the survival curve. So we see this stunning effect by all the vaccines. 5 out of 6 controls died between day 4 and day 7 following challenge, very similar to what we saw in the earlier titration study. One animal did survive, which is we did not see in the earlier titration study, but still 5 out of 6 animals died. And 18 out of 18 vaccinated animals survived. So basically all the vaccines provided protection against mortality. So if there is an H5N1 outbreak, then any of these vaccines should do well. We see differences when we start looking at viral loads. So first in plasma, interestingly, we see all the animals have plasma viremia with H5N1 flu in the sham control group. This is different. In the H1N1, it really was just a mucosal infection. We did not see any plasma viremia following H1N1 infection in macaques. Following H5N1 infection, when we have a clinically lethal model, then we see plasma viremia at about 4 logs levels in 100% of animals in the sham controls. All the 3 vaccines abrogated plasma viremia completely. If we look at virus in the mucosa, in BAL and nasal swabs, we see incredibly high viral loads, 10 logs of virus in the BAL and about 7 logs of virus in nasal swabs. So about 1,000-fold more virus seen in BAL for H5N1 compared with H1N1. And this is abrogated by about 2 logs when we look at the mRNA and the RAD52 intramuscular groups, and it's abrogated drastically when we give the intratracheal boost. Similar for nasal swabs. It's abrogated about 2 logs for the intramuscular boosted groups and about 4 or 5 logs with the intratracheally boosted group. So if we look at this quantitatively and we look at day 2 viral loads in BAL or day 2 viral loads in nasal swabs, we see these incredibly high viral loads in the sham control animals, about 9.5 logs here and about 8 logs here. There's about a 2 log statistically significant reduction of viral loads for the mRNA vaccine intramuscularly and the RAD52 vaccine intramuscularly. And we see this stunning 6.3 log reduction, more than a millionfold reduction of viral loads when we boost intratracheally and we can induce mucosal immunity. In nasal swabs, we see about a 3 log reduction in nasal swabs by the intramuscular boosted groups and a 5.1 log reduction of viral loads in nasal swabs for the intratracheally boosted group. So just this stunning improvement in protection when we can induce mucosal immunity. So this is my last slide, basically the conclusions in terms of correlates protection for influenza vaccines. We showed that mRNA and RAD52 provide superior protection compared with the current clinically licensed vaccines, QIV and FluMist, in the NHP H1N1 influenza challenge model. Immune correlates of protection for QIV and FluMist are serum antibody titers, which is not a surprise because those are essentially the only responses those vaccines induce. mRNA and RAD52 vaccines induce robust antibody and T cell responses, and both correlate with the superior protection observed. And the RAD52 mucosal boosting induces comparative systemic immunity to intramuscular boosting, but substantially improves mucosal immunity, resulting in improved protection against mucosal H1N1 and H5N1 influenza challenges in macaques. So I guess putting it together, we showed that mucosal boosting, as long as there's nothing magic about RAD52, we think that any vaccine that has the biophysical stability to survive on the mucosal surface and that can then prime mucosal responses will likely have the same effect. But what we showed is that mucosal boosting can drastically improve protective efficacy in 3 non-human primate challenge models: SARS-CoV-2, H1N1 flu, and H5N1 flu. And so I'll leave you with this provocative question. These data might suggest a path to improving respiratory virus vaccines. And should future vaccines include both a shot in the arm and a spray or a puff? So this is our group at Beth Deaconess Medical Center, and here are the first authors of various articles I discussed along the way. I'll stop there and have you take any questions.
Excellent. Thank you very much, Dan. That was fantastic. Plenty to digest, and we're already getting a few questions in the chat. But I'm going to take the liberty of starting because I'm the host, and you indicated it on your last slide, the very last line. In fact, I guess I was going to ask the question, if we think, showing that clearly that this intratracheal route seems to be the most effective, what would practically be the way you would do that in humans? Would it be some sort of inhaled type approach? And I guess the follow-on is, would you still be able to achieve, I guess, the load of vaccine that you could give via intratracheal with a device?
Yeah, so I mean, to some extent, these are proof of concept experiments where we can ideally deliver whatever dose we want exactly into the lung. Clearly, intratracheal itself is not going to be the route for humans, but I think the clinical translation will really be one of twofold. First, the intranasal sprays in humans actually do get material all throughout the respiratory system. The intranasal that we did in monkeys is really just drops in the nose. And so that's not really intranasal in humans. So we think that a robust nasal spray in humans, very similar to what you would buy for, say, seasonal allergies in the drugstore, will likely achieve the same effect. We won't really know that until we actually do clinical trials. An alternative option is one could actually have a respiratory vaccine and coat, say, vaccine lyophilized powder on something like an asthma inhaler and use that. We think that would require some formulation, but we think that's entirely within the realm of possibility. We do know that actual aerosolized vaccines have been approved and are being used in China for COVID-19 vaccines, for example. So actual true respiratory, true aerosolized delivery has been used not just at the phase 3 level, but actually for approved products that are on the market. So that's the third option. That's more cumbersome for delivery. So I guess the three options are either a simple nasal spray, respiratory sort of meter dose inhaler, or true aerosolized delivery. And all three are easily done in humans.
Okay, great.
We would not propose to administer the vaccines by an endotracheal tube.
No, completely understand that. Yeah, I was just thinking about because as you mentioned, I mean, there is flu mist, which is already, I guess, an intranasally delivered approach, because that's an attenuated vaccine, isn't it? But that doesn't necessarily, I guess, show outstandingly better immunity compared to the other approaches. So,
I mean, our suspicion is that the flu mist is too attenuated, that
okay.
the importance of safety has made it much less immunogenic. Because theoretically, a live attenuated flu delivered mucosally should raise mucosal immunity, but it doesn't.
Yeah, that's
And,
it. Yeah, it's interesting.
and we think that it's probably because it's overly attenuated.
Okay, yeah, that makes sense. All right, plenty of questions. Kerry Sangram, one of our members of Sydney ID here, has asked, any thoughts on the kind of dendritic cells that stimulate the TRMs? And just to follow up to that is, she's asked, is there a difference between the dendritic cells that are stimulated by IT versus IM with these vaccines, and if that may impact on the resultant immune response?
Yeah, that's really interesting. And we actually don't really know the answer to that question. I think that it's really largely a black box as to how exactly the mucosal immune responses are induced. There was a nice paper in the journal Nature that tried to start looking at the pathways for inducing mucosal immunity. And I think just more work needs to be done. We don't really know if the responses are primed in bronchial associated lymphoid tissue or particular lymph nodes. We don't really know exactly where immune priming happens or the cells associated with it. So, so I don't think we know exactly which types of DCs are important for inducing the resident memory T cells. But it's certainly an area that we're interested in learning more about.
Okay, got a lot of questions, so let's see if we can get through them all. Another question relates to the approach. So, is there value in giving a administration IM and mucosally at the same time, or do you envisage that you would need that gap between the prime and the boost?
That's really interesting. So these three studies, we sort of kept with a similar protocol, in part because it worked and we were trying to address a proof of concept question, which involved the so-called prime pull approach, priming intramuscularly and then boosting mucosally. We've actually done one study that's not yet published. I didn't have time to discuss it today, in which we only delivered the vaccine mucosally, and that also worked. Not as well, but it also worked. So, so we have not really optimized the delivery strategy. Whether you need to have systemic immunity that's somehow pulled with a mucosal boost, or whether they're really just independent, is not really known. But it is clear that if we prime mucosally, and then if we prime systemically and we boost mucosally, we get these incredibly high mucosal immune responses. So I think we would need to do those comparative studies, and we haven't done those yet.
So a question from William Asquith relates to, do you think the lack of induction of mucosal immunity following smallpox vaccine is responsible for the reports of breakthrough infection with Mpox?
So we did some studies on the Mpox vaccine. We have a paper last year that was published in JAMA, in which we looked at the immune responses and the durability following MVA-BN in humans. And that was not done from a mucosal perspective, but what we showed is that the MVA-BN in humans did raise binding and neutralizing antibodies to Mpox. We didn't do smallpox, of course, but those responses waned quite quickly and waned within about 3 to 6 months. And so we think the rapidly waning immunity following MVA-BN, it is a very safe, non-replicating vector, but we think that the responses are wane quite quickly following that vaccine, and we think that's probably the reason for the breakthroughs.
Okay, thank you. Another question here from Tony Cunningham from our institute and from Westmead, Wimmer. Out at Westmead, does your intranasal administration engage the adenoidal lymphoid ring, and how important is it compared to intratracheal admin?
Yeah, great question. So we are very interested in the mechanisms of immune priming following mucosal delivery. I think we have a really nice system where we get a very consistent, very robust mucosal, humoral, and cellular immune response following adenoviral delivery to the mucosa. So it's a really nice system to really study these. We really haven't done a lot of the mechanistic work. We're very interested in doing that, but we don't really know which mucosa along the way, whether it's the adenoids, whether it's bronchial lymphoid tissue, whether it's lymph nodes. We don't really know which lymphoid tissues are engaged, but it's certainly a question that we're asking now.
Okay. And another question relates to the virus itself that you were using in these studies, and do you think the results are especially effective intranasally and IT in macaques due to the nature of the Rad52 being a monkey virus?
Probably not, because the first study I showed used human Ad26, and we saw a very similar effect. So what we can say is we see a similar effect with a human Ad26 and a monkey Rad52 vector. Now, they are likely highly cross-reactive, so maybe it's that both of them are naturally tropic and there's enough cross-reactivity. So it's not specifically a monkey virus. It could be one might rephrase the question, a primate virus, either human or macaque. And I think that's a possibility because these viruses are natural mucosal pathogens. They're natural respiratory pathogens. And so clearly they have the natural ability to infect or transduce, rather in this case, respiratory mucosa. I guess to address the question, you could try the um, say maybe a mouse adenoviral vector in monkeys or something. Well, we actually do have a paper. Come to think of it, I'm just sort of brainstorming here. We have a paper that was published in iScience this year in which we use the same vaccines, mRNA and Rad52, in a mouse model, and we see very similar results. So we know that the Rad52 vector induces similar mucosal immunity in a mouse. So I think I just talked my way into thinking that it's not because it's a primate virus in a primate.
Okay, great. Question from Tanya Golubchik is, thank you for an excellent presentation. As you're aware, annual flu vaccination programs in the UK use a nasal spray, possibly flu mist. And she's asked, is this the way forward? So I guess, do you consider that there'll be much more take up of this approach?
So so I'm actually not aware of, I wasn't aware that that's the standard vaccine. So in the UK or in Australia, do people routinely get the live attenuated nasal vaccine rather than intramuscular vaccine? Because that's different. In the United States,
Yeah.
both pediatric and adults are mostly getting the intramuscular inactivated virus vaccine, but not exclusively. A small percentage of people opt for the nasal spray.
Yeah, look, I'm not aware of the UK situation, but I think Tanya might be across it. In Australia, we don't have flu mist at the moment, but I think it's coming in next year
I see. So
as an
at least in
additional.
Australia, then do most people get the intramuscular
Yes,
inactivated vaccines,
absolutely. At the moment, yes, yes.
including pediatrics?
Yes, I think so. Yeah, because we don't have the flu mist as yet.
Yeah, so I'm not aware what the pediatric vaccine policy is in the UK, but assuming that's accurate, then I actually am not convinced that's the way forward because I personally think that the flu-mist vaccine is probably overly attenuated. I think it's a good concept, but I just think that it has not shown substantially better efficacy than the intramuscular inactivated virus vaccine in empiric clinical trials. So I'm not convinced that's necessarily the way forward. I think that what we need is really a quantum improvement in flu vaccines that's not available, that's not possible with any of the current clinically licensed products.
Hey, Caroline Ashley from Sydney Ideas asked, how do you plan, or how would you envisage you would be able to measure mucosal T cell responses when you move these products into clinical trials?
Yeah, that's really interesting. So in a clinical trial, it's easy to measure serum antibodies and not too hard to measure peripheral blood T cell responses.
Mm.
And it's also, relatively easy to do nasal swabs or nasopharyngeal swabs. And we have methods in the lab that we can very routinely measure mucosal antibodies in humans. But there's no easy way to measure mucosal T cell responses in humans. So I would imagine because we've tried in both human nasal swabs and in macaques, and we just don't get enough cells from a swab. The cells we do get, um, the cells we do get are mostly published a nice paper where he has in some cases been able to get enough cells from human nasal swabs, but I think they do sort of deep nasopharyngeal swabs, And then he has methods that can handle very small numbers of cells. So it is possible, and we'd probably try to use some of those techniques that were developed by Shane Crotty and others.
Mm.
You know, from a laboratory perspective, you would love it if you can maybe do a sub study and actually do bronchoalveolar lavage in humans. And I think in a small number of people, you could do invasive procedures like that, but certainly you wouldn't do that on a large scale. So I guess the short answer to the question is it's hard. Probably a first phase 1 study probably would settle for mucosal antibody responses. And then in a subsequent study, if the vaccine is looking promising, probably would do some nasopharyngeal swabs with the newer techniques that can use very small numbers of cells, and possibly a sub study where you might be allowed in a small number of people to do some more invasive procedures in humans like BALs.
Okay. And just on the last question about, sorry, the last point about flu miss, Tanya and Terry Nolan from Doherty have just indicated that the UK program is with the live attenuated virus in children only. In schools, coverage around 60%, and flu missed in Australia in 2026, but only in private markets. So that's where we are.
Good to know. I learn something every day.
Yeah,
Thank
no,
you.
it's good to know. We've got a couple more questions and a couple more minutes, so let's try and get them all in. Annalise Ashurst says, thank you for your presentation. Were there any notable findings regarding reactogenicity or adverse findings in the NHP models with using any of these vaccines?
There were no adverse findings. The animals were fine. There was no respiratory distress, no adverse consequences. Now, of course, the studies are not specifically designed as safety studies, but there was nothing evident by standard, veterinary sort of twice daily observation.
Okay. And the last question, I think we've timed it perfectly, Dan. Is there a difference between mucosal immunity induced by respiratory delivery or by gastrointestinal delivery? Since the lower respiratory tract is more challenging in practice, should we consider exploring gastrointestinal routes, such as anal delivery, what they've mentioned here?
It's interesting. On a practical level, then I can't really envision, if I put my clinical hat on, I can't really envision a widespread vaccination program using GI or GU routes of delivery. It certainly could be done in a clinical trial setting. Um, we have some very early data, which is similar to a number of publications showing that if we give a vaccine by the intranasal route, this is in mouse data, then we actually can induce responses in the GI and the GU tract. So it's interesting. So there is some sort of mucosal crosstalk. And there are published papers from a number of groups showing the same thing. We haven't really explored the reverse. We haven't really explored delivering a vaccine by the GI or GU routes and looking in the respiratory mucosa. But we know that there is some mucosal crosstalk, so I wouldn't be surprised if that's the case. We haven't really explored that because it's not clear to me that there could be much clinical applicability of that. Maybe I'm wrong. But certainly intranasal delivery is widespread. People use intranasal sprays for seasonal allergies and many other indications routinely. Asthma inhalers are common. So you can definitely give things orally by the respiratory route and intranasal route in a very easy way.
Yeah, I know there were some studies giving, I think some ADNO studies giving orally, but it doesn't seem to give great immunity within the respiratory tract. I think, I think
Yeah,
it's
I
not.
mean, the classic example is the military Ad4, Ad7 vaccine, which is given as an oral enteric-coated capsule
Hmm.
and gives very good protection against severe respiratory disease with Ad4 and Ad7. And that was a US military vaccine that works very, very well. So that's an example. But I think the challenge is that any oral vaccine, and there are several examples, has to get past stomach acid. So it has to be fairly robust and probably enteric coated. So,
Yeah.
the oral polio vaccine is the classic example, I would think.
Okay. Okay, well, we are time, and that was a really great, well, a fantastic presentation, and I think a really engaging question and answer session and discussion. So just remains to thank Dan for joining us, and thank you all for joining online and for your interaction with this seminar, and we look forward to welcome you all at the next seminar. So thank you to everybody, and thank you very much, Dan, for your presentation. We hope to
Thanks very much. Appreciate all the questions. Thank you.
All right. Thank you. Okay, we'll log off. We'll chat soon.